let's take a look at this graph y equals f at x that we can see here in red, and let's see what we can do to turn that into this graph of y equals g at x. And what we're going to do is we're going to describe the transformations in order, of course. We're going to express using mapping notation, and then we're going to write out what the new equation would be. Now, for me, I can't do one without the other. In other words, I can't tell you the transformations that have been applied without using mapping notation. So really, you're going to see I approach these using the two of them together. All right, so we're going to go from red to purple is the key here. And in this case, since we have a definitive beginning and definitive ending, we're going to compare the domain of f at x to the domain of g at x, and likewise for the ranges of those as well, and see what kind of changes we have. That'll help us with some of the stuff, and then looking at visual inspection, just looking at the graph will help us with the others. So let's go ahead and consider that domain of f at x. So we have -4, and that's going to take us to 10. And if we consider the domain of g at x, I can see here it looks like we're at -7, +7. Okay, fantastic. So we have got ourselves the domain of f at x. We've got the domain of g at x. How can we use that domain to help us? Well, domain has to do with the x has to do with the horizontal. So we're going to use this to see, has a horizontal stretch been applied? So what I'm going to do is consider my domain of f at x. If I start at -4 and I span all the way over to 10, I can see that this whole graph is going to take up a length of 14. Or you could just look at this and see that, okay, that's going to be 14 units wide. Likewise, if I take a look at g at x, I can see -7 to +7. I can see pretty quickly that's going to be 14 as well. So what does this tell me? By comparing the domain of the two, I can see that there has been no horizontal stretch factor about the y-axis. Perfect. So now that I've done that, I'm going to do the same thing for the range. I'm going to compare the respective ranges of these two. So we have a range of f at x going from 1 to 7, and we can see a range of, and if I compare the range for g at x, it looks like we're going from -8 to +4, which is going to span 12 units. Well, I'll take what I start with, 6 units, and I'll work down here in the bottom left. So if I had 6 units and then I have a vertical stretch factor, when I was done, that would give me 12 units. We know that good math is we'll divide both sides by 6, we'll cancel that, and we're left to see that, hey, it looks like we have got a vertical stretch factor of 2. Okay, and so up here in the top right corner, we can say that we have a vertical stretch factor of 2 about the x-axis. Well, I think that's about it for the domain and range. So what I'm going to do now is start to use visual inspection. And so as I take a look at this, I can see that I have at least one reflection. I can see I've got a ramp on the left and I've got an arm kind of curving on the right. And likewise, I've got a ramp on the left and an arm curving on the right. That tells me there has been no reflection over the y-axis. I have not reflected this over the y-axis because it's got the same thing happening in both cases. At the same time, I can see that I have reflected over the x-axis. I can see one ramp is rising, one is falling. Likewise, I've got an arm curving up and an arm curving down. I can see I have got a reflection over the x-axis. So that's where the visual inspection part comes into play there. What we now need to figure out is if there's been a shift of any type. We know we've stretched this, we know we've flipped this, but have we shifted it? It looks like it. Well, that's why I said here, I've got to deal with these two components together. I've got to state the transformations and express using mapping notation together. How? Well, first of all, let me get down these transformations that I do know. We have got ourselves a vertical stretch factor of 2 about the x-axis, and we have a reflection over the x-axis. So we have those two things going on. The big thing is we have to make sure we shift last. So what I'm going to do is take these two transformations and begin a partial mapping notation. I should have here xy maps to. Now, no stretch and no reflection has been imposed upon the x, so that's just going to be an x. I do know, or I do suspect there's going to be a shift of some type, so I'll put a plus h here. And then for the for the y, we see we've got a vertical stretch of 2. So that's going to give me a 2y, but I've also got a reflection over the x-axis, which means I'm changing the sign on the y. So that'll be a negative 2y. Again, I don't know if there's been a shift, so I'll put the plus k. Look at your graph. Well, look for a nice key point that you can easily identify. I can see a couple. I can see this pink corresponds to this pink. I can see this green to this green. Well, I think what I'm going to do is just take the first one I saw, that pink point. If I take a look at the pink point on f at x, I see that point will be called 10, comma 7. And that's going to correspond down here to 7, comma negative 8. We are going to go from 10, 7 on f at x. And when we're done, that is going to have become 7, negative 8. Now that's of course after we've applied our stretch and our reflection. And this is why we have to go to the mapping notation. Okay, well, let's start with the easy one then. Let's start with that x coordinate. So what I'm going to do is take x and I'm going to take x plus h. I'm going to take this partial mapping notation and separate it a little bit more. I'm going to say x is going to become x plus h. And what I'm going to do is I'm going to take this 10 and I'm going to sub it into the original 10 here. And I'm going to put it into this one right here. And by the time I'm done, when I'm done with that, it's going to have turned into 7 is what's going to have happened. So 10 plus h is going to equal 7. Now you might find this part distracting, so we can just ignore that. Well, that's the 30-1 thinking. Now I can take a look at this graph and apply some more simplistic algebra, if you will. Let's subtract a 10 from both sides, and we're going to see here that h equals negative 3. That would tell me I had moved 3 units to the left. So I now have another transformation to apply here. We also know 3, we have shifted 3 units left is what's happened. And so with that mapping notation, this now becomes x minus 3, comma something. X comma y is going to yield x minus 3, and then we know we're going to have a negative 2y, but we're not quite sure what the rest of that is going to be. Okay, we know we're going to have y, negative 2y, but we don't know what the k value is going to be yet. So we're going to do the exact same thing again. And let's go back to our coordinates up here. And once again, let's go from the 7 to the negative 8. So we start with a 10, comma 7, and then by the time we're done, it's going to turn into a 7, negative 8. And so how are we going to do that? So I'm going to use the y component of my partial mapping notation here. And you see I've switched to this darker color. So y is going to map to negative 2y plus k, and by the time I'm done, it's going to equal negative 8 is what's going to happen. So that negative 8 is going to end up there. I don't care about the 7. I don't care about the 10 because that was the x. I already dealt with that. And this 7 is going to go here. And technically, I could put a 7 right here as well, but I don't know that I really need that. All right, negative 2 times 7 is going to be negative 14 plus k equals negative 8. We're going to add a 14 to both sides, and it turns out we didn't shift down 15 units because k turns into a positive 6. We shifted up 6 units is what's happened. And so right here we'll have a plus 6 as well. So you can see step 3 could be shifted 3 units left and 6 units up. The big thing I'd be looking for here is you have demonstrated in the correct order that the shift is going to come last. So we know to always shift last, and pardon me as I shout, always shift last. So we now see our transformations in the correct order. We now see our mapping notation. And then lastly, let's go ahead and write that new equation of g at x. Through the beauty of math. And just like that, y equals negative 2g at x plus 3. I have now written the equation of the transform function g at x. I have stated the transformations in the correct order. And I have also, let's get crazy and go with green, express this in mapping notation as well. All right, so there we have identified the transformations that have turned one graph into the other graph. So as always, good job, good luck, and goodbye.